Welcome back to Maths with Mrs. J. I'd now like to start talking about area under a curve and how we use a definite integral to do that. In class, you will probably investigate the difference between what's called lower rectangles and upper rectangles, and you might well do what's called the trapezoidal rule. Having a graphics calculator or some sort of computer program to assist you with that is very, very helpful, because the thinner the rectangles, the more accurate you'll be. I'll just explain a little bit about what we're doing there, and then I will show you how to do it with a definite integral. So if we're talking about this area under here, we can obviously divide that into sections according to equal width sections. Now, I'm going to be very rough here and just say 3 sections, all right, for whatever it may be. If we have what's called the lower rectangles, they're the ones with the smaller value of y for each rectangle. So obviously, if I have the smaller rectangles and I work out those areas, so I'm doing this width times f at this x value, this width times f at this value, and this width times f at this value, and adding them up. Obviously, in this sort of example, they will be less than the area required. Similarly, if I were to do the upper rectangles, so if I were to go with the bigger y value each time and multiply, then what I've got is obviously going to be bigger than what is required. An even better estimate is to do the trapezoidal rule. So what we can do is we can draw a secant from each of these points to the next point. And what we've got is a trapezium, haven't we? We know how to find the area of a trapezium. It's half the sum of the 2 parallel sides multiplied by the perpendicular distance between them. And what actually happens is you end up with function of x at your beginning x value, this length at your end x value, right? So you have one of those and one of those, and what you'll actually have is 2 of everything in between. So you'll have your first and your last, you'll have 2 of everything in between, because once for this trapezium and once for this trapezium and once for this trapezium, and then you're going to be multiplying by that width. Clearly, the more rectangles or trapeziums we divide it into, the more accurate it will be. So if you're going to be using your graphics calculator to use the trapezoidal rule, obviously, the more trapeziums you divide the area into, the more accurate you're going to be. Now, let's get back to actually doing it in the perfectly accurate way, which is using integrals. We can use a definite integral to work this out exactly. So in this example, all we need to do is do the definite integral from 1 to 3 of this function. That's all we need to do. So let's do that. So area is going to be from 1 to 3 of x squared plus 1, the integral of that. So we do our normal definite integral, so x cubed on 3 plus x. Okay, so we're going to get 3 cubed on 3 plus 3 minus 1 cubed on 3 plus 1, which is what? 12 minus 1 1/3, which is 10 2/3 square units. If you were to try the trapezoidal rule with that and only had 2 trapeziums, you're obviously not going to be fantastic, but it would be at least an estimate. If you were to have, say, 10 trapeziums, then you should be pretty close to what we get using our definite integral. Okay, let's press on to the next example, and this is where a diagram is really important. So let's head over to our next example. The first question just says, evaluate that definite integral. They're not saying anything about area, we're just saying evaluate that definite integral. Okay, all right. So the integral of sine is negative cos. All right, so we're going to get negative cos of 2 pi minus negative cos of 0. Cos of 2 pi you should know is 1, and cos of 0 is also 1. So we're going to get negative 1 plus 1, which is 0. All right, we get 0 as our definite integral there. Okay, now let's consider the difference between that question and what we're asking in our next bit. What if we wanted to find the area bounded by the graph of y equals sine of x, the x-axis, and from x equals 0 to 2 pi? Okay, well, let's draw a little sketch and see what we're dealing with here. So we've got y equals sine of x. We should know roughly what that looks like. It goes up to 1, down to negative 1. It has a period of 2 pi, so pi on 2, pi, 3 pi on 2, 2 pi. When x is 0, sine is 0. When x is pi on 2, sine is 1, etc. So we get this kind of shape happening. It's a little bit hard without a pencil, but I'll do the best I can. All right. So you get roughly what I mean there. So that's y equals sine of x. Now, if I actually wanted the area bounded by that function, the x-axis and those values, what we're actually wanting is this section in here and this section in here. Clearly that is not a 0 area. So clearly just doing our definite integral is not going to work. It was fine for that question because we were just asked to find the definite integral, but we can't use it as is to find our area. What actually happens is when your graph dips below the x-axis, that's a negative with your definite integral. So these cancel out. So that's why we got 0, because see how this function, you got the same amount above as you have below, between 0 and 2 pi, and that's why you're going to get 0, because they're going to cancel each other out. You're going to have one positive section and one negative section, and they will add up to give you 0. So how do we combat that? What do we do? Well, several ways we can do this. I would, to be honest, just use the fact that this section is exactly the same as that section in area, and I would just say, well, our area is twice from 0 to pi of our sine of x dx. So it's twice our negative cos from pi to 0, whoopsie days, which is twice, okay, so negative cos pi minus negative cos 0. Cos of pi is negative 1, so negative cos of pi is 1, and this is 1. So we get 4 square units. You can, alternatively, and this is what you will have to do in a situation where those two areas are not going to be the same, you would do area is from 0 to pi of sine of x dx plus the absolute value of the next section, so from pi to 2 pi. Or you could even say, well, I know that's going to be negative, so I'm going to swap my pi and my 2 pi. Remember, from A to B is negative from B to A. So if you know it's going to be negative and you want to turn it into a positive, you could just swap those values there. Okay, so basically the takeaway from this lesson is if you are trying to just find a definite integral, go for it. Do your integration, sub in and subtract. However, if you are using definite integrals to actually find an area, you do need to have a sketch. You need, or at the very least, to have an idea as to where the function is, where it's crossing over the x-axis, because if it dips below the x-axis, that part will count as a negative and will counteract this area here, and you might get an incorrect result. For example, here we came up with 0 because they were both the same areas, but one was positive and one was negative. So if you need to actually calculate the area, you'll need to get a sketch, and you'll need to, obviously any bit that's below, you'll need to take the absolute value of that.